Alright, hello. What we've got here is a discussion of logarithm, and it's going to introduce the topic. Um, Keep in mind, this particular video is just a quick review of some of the major ideas, so I'm going to try to go quickly, understanding that you need to spend some time thinking about these ideas. I'm simply laying out the facts, and then it'll be your job to absorb them. Prior to understanding the word logarithm, we studied exponents, and one of our tasks was to look at numbers and express them as powers of something. So these are all powers of 2. We could write the number 4, for example, as 2 squared. We could write the number 8 as 2 cubed. 1/8 would be 2 to the negative 3. So that was one of the kind of exercises that we did. Essentially, what we're doing is we're asking about the exponents that let me start over. If we're writing as a power of 3, we are looking, when we see the number 27, to find the exponent on 3 that produces 27. So in other words, I'm asking, the power on 3 of 3 to the x is the power on 3 of 9. So in other words, and that's just a lot of fancy language to say, 2 is the power on 3 that produces 9. Similarly, 5 is the power on 3 that produces the number 243. So, if you think about, the original question where it says write as powers of 3, 27 is written as 3 cubed. I'm going to modify the question slightly and just focus on the exponent itself. What number on 3 makes 27? And the answer is 3. What number as a power on 3 makes 243? The answer is 5. As you can see, it's kind of cumbersome. It's a lot of words to put together just to be able to ask what is the exponent that makes the number. So what mathematicians have done, and this goes back several hundred years, so we have no say, is introduce the word logarithm, which essentially means arithmetic number or proportional number from the Greek. And instead of actually using all the words that I used here, the power on 3 of 3 to the x is the power on 3 of 9, I can simply replace all of that verbiage with the log base 3 of. So the log base 3 of is just the mathy way of saying the power of 3 of. So before, when I asked you to write 9 as a power of 3, now I can write it as what is the log base 3 of 9, to which the answer would be 2, because with the log I'm just asking about what is the exponent. So the log base 3 of 243 is 5, for the same reason that 243 is 3 to the 5th power. The idea behind logarithm is, it's kind of funny. What we've done is we've intimidated students because we don't introduce this until later in high school or earlier in high school, and so it's automatically intimidating because it must be a difficult high-level math concept. It isn't. It's just I can't even honestly tell you why it's delayed, but the fact is we use symbols all the time to basically define an operation that requires too many words to say. So, for example, absolute value. That's a lot of, well, it's not a lot of words, but it's a lot of syllables, and instead of saying the absolute value of, we just put 2 vertical bars around the number, and it says that. More importantly, the absolute value is actually asking for the distance your number is on a number line from 0. So, if I wanted to avoid using absolute value symbols, then anytime I wanted an absolute value, I would have to use the phrase, the distance of the number from 0 on a number line. And I'd rather not do that. Here, this is called the square root. Square root is shorthand for the number which could be multiplied by itself to produce the number inside, or something like that. My point is, rather than use all those words and confuse everything with the English language, we cut straight to the symbol itself. So sine is a symbol. 3 as an exponent is a symbol. This is a symbol. This is not double absolute value. It's called greatest integer function. You don't have to know what it means, but just understand that we use symbols all the time in mathematics to define operations. So how far is a number from 0? What's the square root of a number? What's the cube of a number? What's the sine of a number? What's 3 times a number? In the same way, logarithm can be used. So in other words, log is just another operator, just like square roots or multiplying or signing or whatever. So instead of asking right as powers of 2, we're going to actually ask directly for the exponent that produces a number. So the exponent on 2 that gives me 2 is 1. 1 is the exponent on 2 that produces the number 2, and so forth. So the log base 2 of 4 is 2 because 2 squared is 4. The log base 2 of 8 is 3 because 2 cubed is 8. The log base 2 of 16 is 4 because 2 to the 4th power is 16. The remainder of these, of course, these are all fractions. Each number here is less than 1. The closer we get to 0, the more negative our numbers become. So if negative 1 was a power on 2, I would get 1/2. If negative 5 was an exponent on 2, I would get 1 over 32. That leads us to this language of logs, and what we should be able to do is transition in our mind and be fluent in this language. We should be able to transition between multiple forms. You see what this says if I read this. A is, log means exponent, so I would say the exponent on base B that produces the number m. A is the exponent on B that produces m. Now I'm going to go over here and look at this statement and see if I can make it feel right. A happens to be the exponent on B that produces the number m. So these are actually inverse forms of the same expression. The way I compare it or think about it in my own crazy brain is how the concept of the square root of 25 is equal to 5, just as 25 is equal to 5 squared. So I could take the square root of 25 and make it equal to 5, or I could square 5 and make it equal to 25. Squaring and square rooting are inverse operations. Similarly, I can take 3 to the 4th and make that 81, or I could say the log base 3 of 81 is equal to 4. So you can say it one way or you can say it another way. They're just inverse ways of describing the same truth. So we have logarithmic form and exponential form. We have square root form and squared form, inverses. Anyway, I just want to get rid of some of this stuff here. The practice then is we would like to get fluent and be able to perceive logarithm the way it says. For example, when I see the log base 3 of 9, I'm basically, and by the way, that's how you say it, the log base 3 of 9. And if I'm looking for the log base 3 of 9, it's easy for me to see that 3 squared is 9, so the exponent would be 2. So I can do that, y equals 2. And similar, I can do the same thing for the remainder of these. I know that 5 cubed is 125, so the exponent on 5 is 3. 2 to the 5th is 32, so the exponent on 2 is 5. I can do that stuff just by reading. But we get something like this, maybe I get my head crossed and it gets a little confusing. So one of the tools that you have is this ability to invert the expression into something a little bit more familiar. I like this exponential because I've been working with that more. So when I see log base 10 of 1/10 equals y, I remind myself that y happens to be the exponent on 10 that produces the number 1/10. Which I remember then 1/10 is really 10 to the negative 1, and then I can see the exponent on 10 that gives me 1/10 is negative 1. So y is negative 1. Similarly, I'm asked to find the log of the square root of 7, log base 7 of the square root of 7. You may or may not recall that the square root of 7 is really 7 to the 1/2 power. So the exponent on y that produces the square root of 7 happens to be 1/2. So y equals 1/2. And in the last exercise, that can be really complicated for some people, for others, I mean, it all basically depends on your skill set. But the question again is, y happens to be the exponent on 1/2. Y happens to be the exponent on 1/2 that produces the number 4. I don't know what to do, so I just mess around, and I remember 1/2 is really 2 to the negative 1, and that's where I say 2 to the negative y is equal to 2 squared, and that means negative y equals 2, or y equals negative 2. One other notion that came out when we were working on this for the last few days was the idea of inverse operations. What happens when you apply an inverse to itself? To give you an idea, what if I took a log and made it into an exponent? After all, logs are exponents. What if I made an exponent an exponent? Crazy. Well, here, we got 5 to the log base 5 of 25. I don't know. I'm confused. But here's what I know. The log base 5 of 25 is 2. So 5 to the log base 5 of 25 is the same as 5 squared. And 5 squared is 25. Holy crap, I had the 25 was inside the argument here. I do a bunch of stuff and I end up with 25 at the end. It's as if the log base 5 and 5 to the x are undoing one another and we get right back where we started. 8 to the log base 8 of 1 is equal to 8 to the, well, I have to figure out what log base 8 of 1 is. That's 0. 8 to the 0 is 1. So here's one. The log 6 to the log base 6 of 8. Now the problem is, that is 6 to the, I don't know. What is it? Well, but the thing of it is the exponent on 6 that gives me 8, I don't know what it is, but I'm going to take that exponent and put it on the 6. And so if I take 6 to that power, I'm going to get 8. The exponent on 6 that gives me 8 is the exponent on 6, so it will give me 8. Or in other words, you just look at it. If the bases are the same, you will undo each other and end up where you started. Here's the mathematical way of stating what I just said, and it's a lot cleaner. A to the log base A of m is m. Because they're inverses, they undo one another and clean up. Down here, I just wanted to illustrate that using the language of logarithms, again, can be really handy for some of the exercises, like the log base 4 of x equals a half. If you don't know how to think of that through reasonably, then translate it into exponential form. Then you can see 4 to the 1/2 equals x, therefore x equals 2. Similarly, 2 to the x, log base x of 2 equals 4 means x to the 4th equals 2. It's not really obvious what x is going to be. So there we can see we take the 4th root of both sides, so x is the 4th root of 2, or x is 2 to the 1/4 power. Finally, just one last concept, and that is a really straightforward thing, but for some reason this makes people, gives people difficulties. I don't understand it, but basically there's synonyms here. If you ever see the log and there's no base there, like for example, if I see the log of 100, then I'm just going to treat that as a base 10. It's implied as a base 10. We call that the common log. Similarly, if I see the ln, which stands for natural log, if I see the natural log of x, I should just understand that that's log base e. Log base e and natural log are the same thing. So when I see natural log of e, I'm really saying what's the exponent on e that gives me e, the answer to which is 1. And here, well, here it's saying 2 is the exponent on e that gives me x. So what would x be? Well, let's write it out again. 2 is the exponent on e that gives me x. And again, what is x? E squared. Simple. Similarly, 1/2 is the exponent on e that gives me x. What is x? Square root of e. Crazy. See what I did there? Alright, so, the rest of these exercises are all just sort of getting around the same general understanding, but I just wanted to point out in these last two exercises that you have to use your properties of exponents to be successful in some cases. So this is not just a introduction to logs, but it's also a review of exponential properties. Log of the cube root of 100, for example, can and should be expressed as, again, remember it's log base 10, of 100 to the 1/3 power. Now remember, because the base of the log has not been expressed, we're going to assume that that's base 10, and 100 is a power of 10, so I'm going to write this as the log of 10 squared to the 1/3, which then becomes the log of, using power of a power, 10 to the 2/3. So the exponent on 10 that gives me 10 to the 2/3 is 2/3. So don't forget how to use your properties of logarithms, or exponents rather, because you'll need them to help you evaluate logs. This is a long enough video. Thanks for watching. Have a good day.